Hey folks, welcome to another system design problem breakdown. Today we're going to be talking about how to design Facebook post search. This is a really interesting infrastructure question around organizing data, enabling scalability on both the read and the write path. Lots of interesting stuff to talk about. This is also a favorite problem of mine because it was actually asked of me in the Facebook interview that I had years ago. So I have firsthand experience with answering this question. Just by way of introduction, I'm Stefan. I'm one of two people who you'll likely run into on this channel, and we are Hello Interview. We're here to help you prepare for your software engineering interviews. We have a lot of system design and behavioral interviewing content on the channel. And if you're interested in that, or if you have interviews coming up, highly recommend that you subscribe. But I don't want to delay any further. Let's go ahead and get into it. Like all of the problem breakdowns that we follow on this channel, we're going to be following the Hello Interview delivery framework. This framework is set up in such a way that it helps you to keep track of your progress as you build out a solution, but also it can keep you from getting stuck. In a lot of cases, through mock interviews, and we've conducted thousands at this stage, what we find is that candidates who have a structure are so much more likely to actually complete the interview and end up with a higher decision, in part because they don't get lost along the way. So the steps of this delivery framework are pretty straightforward. First, we're going to start out with our requirements. We're going to clarify with our interviewer what the scale is, what are functional requirements, so on and so forth. Our core entities discussion is going to establish some nouns that we can use both in our design, but also to set up our API. And our API, in some sense, is going to be the contract that the rest of our system needs to obey. In a good scenario, our API is reflective of the requirements, and we can just make sure our system implements that API. In some data processing heavy problems, it can be useful for you to build out a data flow. We're not actually going to do that here because the data flow is relatively straightforward, but you might see this in problems like web crawler as an example. Our high-level design is where we're going to try to satisfy the functional requirements as simply as we can. It's not necessarily a problem if you jump a little bit ahead and start to bring in some optimizations, but we would encourage you to try to do this as simply as possible, in part to avoid premature optimization and getting stuck going down a rabbit trail that's not actually going to help you build out the problem. The final step for us in the remaining 10 to 15 minutes of the interview is going to be the deep dives. This is in some sense where you're going to spend a lot of time in non-functional requirements, but it'll also be a place where your interviewer might proactively ask you questions about additional functionality or things along those lines. It's important that you leave time in your interview for these deep dives because otherwise your interviewer may want to ask you additional questions, and if you're not done with the base functionality, that might be a problem for the overall evaluation. So we'll follow this structure as we walk through this problem so you can see approximately what this would look like if this was a real interview setting. Our interview is going to start with our interviewer laying out an ambiguous question for us to solve. Oftentimes they'll do this orally, but sometimes they will just paste it onto the screen. In this case, we are going to be designing Facebook post search. In this case, our interviewer is going to add a constraint to the problem. And this is very popular for interviewers to do. They might give you a constraint like we need to operate on only Raspberry Pis. Or they might give you an additional constraint, which is you can't use certain technologies. The idea here is to kind of throw you off of maybe some of the most established solutions to these problems and really understand how you can reason from first principles into a solution. So this is a very realistic representation of this problem, and one you might want to keep in mind as you're preparing for your interviews, that it's not enough to just know that a particular technology applies. In some sense, it can be helpful to know how it works under the covers. The first step in our process is we're going to start to establish some functional requirements. Functional requirements are where we're going to have the back and forth with our interviewer to try to clarify what it is we're actually building and then what does it need to do. Functional requirements are usually best tackled by putting yourself in the shoes of a user or a client and then trying to figure out what are the functionalities that they may need. So in my mind, I'm going to start to picture a search result page and then think about what are the features and functionality on that page. My first functional requirement is probably about how the data got onto that page in the first place. It's possible for you to just take this for granted and assume that, the posts are already created, But sometimes it can be nice to note that users must be able to create posts. I'm also going to note that on a lot of search result page, there's oftentimes something that we want to sort by. In the case of Facebook posts, we probably care a lot about how recently the post was created, and then also how engaged it is. When people upvote and make a post go viral, those are oftentimes the most interesting posts, whereas Jan posting her random opinion may not be what I actually want to see in my search results page. So I'm going to add a requirement here for users are able to like posts as a way of adding that information to the picture. You'll note that here I'm hitting on two functional requirements that are on the write path, not just the read path. It's oftentimes easy to think about systems like search as read-only systems, but in fact, oftentimes they actually have more writes than they have reads, in part because there's a lot of information for us to index. And so it's really important that we think about that write path as we're designing the system. The last requirement is pretty obvious. Our users should be able to search. But with respect to search, there's a lot for us to explore. So if I imagine that search results page, oftentimes on the left-hand side, there are things called facets, or basically filters that I can apply to the search. I may ask my interviewer, do I need to have filters? And they might tell me, no, let's just do keywords. In that case, I'm going to go refine my functional requirement and say users should search by keyword. Another thing that I might expect on a search result page is the ability to sort. And so maybe I can sort by recency or by likes. I'm going to ask my interviewer, do we need to sort by other factors? Do you want me to be able to search by author or sort by author? And they might tell me, let's say likes and time is fine. So I'm going to add that to my requirement. Search can have a lot of other functionality that's kind of buried. So like one that many candidates will come to is, should I be able to support fuzzy search? Or if I typo the keyword, do I expect it to match things that I've typoed it to? In this case, my interviewer is going to tell me no. Another thing that we might ask our interviewer about is whether we should be able to support personalization. That being, if two users submit the same search request, do they get the same results or do they change based on the user? The worst part about personalized search results is you really can't cache them. If I cache personalized search results, I'm really only going to be the other person who's going to read. If I search the same thing twice, maybe I'll see the same results. But if the results are not personalized, the entire world might be searching for the same thing, and they're all going to be able to feed out of that cache. So having non-personalized search results can be really useful. Now, at this point, I've discussed a lot of requirements. I've talked with my interviewer about different characteristics of a search system, and we've got some good starting points. So I might ask them if there's anything that I've missed, and I'm going to keep moving. The next thing we'll talk about are our non-functional requirements. If the functional requirements are what the system ought to do, the non-functional requirements are how the system does this. For a lot of people, they're going to be thinking about things like CAP theorem, about latency, scale, throughput. Those are all good prompts for you to think of good non-functional requirements. Another way to do this is to go through your functional requirements and try to figure out what non-functional requirements might apply to them. Remember earlier we talked that there's kind of two legs here. We've got our writes and our reads. And that might be a really useful thing to ask yourself, what are the requirements on those writes and reads? So let's talk about a few of them. We'll actually go in reverse order. We'll talk about the reads first. So when you do a search, we would expect it to be low latency. It's not really useful if you just say low latency because a big question is how low. Low latency could be a minute for some applications, maybe if you're doing submissions of taxes to the IRS. And for other applications, low latency is microseconds. So it's useful for us to throw out a number here. I'm going to choose 500 milliseconds. And the thinking for me is if it's 30 milliseconds, this is like the frame rate for a movie as an example. Those are going to be things that are borderline imperceptible to people. We don't need it to be that fast. On the other hand, if this was a 5-second search system, our users are probably going to get bored. They're going to disappear. So it's going to be really useful for us to have some middle ground between the two. 500 milliseconds is a nice round number that seems pretty fast, but acknowledges that search is kind of heavy. No interviewer is going to lose their mind. They may correct you on whether you get this estimate right. But having a number here allows us to start to reason about other choices we're going to make downstream. And so it's really important that we have it. The second thing that we're going to talk about for the read side is just the throughput. And in this case, we are expecting a lot of users. You may defer how many users are actually going to appear here. We could do some calculations on what that is. But generally speaking, we've got billions of users and some of them are going to be searching. So we really are expecting a lot of searches to happen. Let's talk a little bit about rights. So when users create a post or create a like, they expect that to eventually appear in the search results. Do they expect it to appear instantaneously? No, they probably don't. In this case, an eventually consistent system is probably acceptable. In the CAP theorem, the trade-off here is we would prefer a system that's high availability over strongly consistent. And most search systems are like this. In fact, if you go and tag Elasticsearch as a CDC on your database, it will be eventually consistent with the data that you're writing. And so eventually consistent is a good way for us to think about it. But let's go back to this idea that we should probably put some numbers on this. Eventually consistent means at some point in the future, but we'd ideally like to put some bounds on this. Expectations from our user might be that we have a post appear in search results within 1 minute. I think this is a nice trade-off here. Basically, it means that if you go to the search a couple minutes later, you're definitely going to go find your post, but you shouldn't expect your post to appear immediately. And that aligns with the expectations of most users. Your interviewer might give you different quantities. Again, that's okay. You don't have to nail this down, but this helps us to reason about things like caches and queues and other things that are going to introduce latency in that eventually consistent write. The next thing that we might talk about is how much approximation we will allow in a system like this. For search systems, oftentimes there is this trade-off that we will not have complete what they call recall over all of the documents that we're searching over. The reality for most search systems is the number of things that you can search over is very, very large, and you probably care about getting a good enough result as opposed to getting the exact result you were looking for. Now, that's not always the case for all search systems, but for many, it is true that you just need a good enough result. And this might be a discussion that we have with our interviewer here. Do we need to have complete coverage or recall? And in this case, our interviewer is going to say, we should have high recall and try to get all of the posts. The last thing that we might talk about is whether or not this system needs to be fault tolerant. I would say that search functionality is really important for a lot of applications, and especially platforms like Facebook. They really do expect these search systems to be up most of the time. But amongst all of the failures, if you were going to fail in creating posts or you were going to fail in comments, search would be further down on the list. Let's go ahead and assume that we need high availability for this system, which maps to our eventually consistent requirement that we came up with earlier, but we don't necessarily need this to be, 7 nines of availability. It's just not that important for the business. So here we've got some good functional requirements. We've left the TBD in terms of our scale, which we'll get into in a second. And that's the end of our requirements discussion. We're going to keep moving. In the non-functional requirements, I put TBD for the throughput of my system. And this was because it's kind of hard to just rattle off an estimate for what the throughput of the system might be. I, of course, could just throw out a number, but I more likely have kind of some unanchored quantity versus something that maybe if I thought about it for a second, I'd come up with something better. For Hello Interview in general, what we find is that candidates will waste a lot of time with estimates that aren't going to be particularly relevant for their problem. But we do find estimates to be useful either electively when you find a part of your design that seems like it might be either a bottleneck or have very large space requirements or otherwise cause you problems. That can be a really good point for you to inject some estimates. It can also be really important for you to try to build these estimates when you aren't sure the overall shape of the system. So for this system, I might naively think it's a search system. It must have lots of reads. But let's go ahead and vet that and see if that's actually accurate. So first, we're going to estimate the number of users. I'm just going to assume that there are 1 billion Facebook users. I think it's closer to 2. Who knows? Then let's talk about let's do rights first. Let's go with rights. So what kind of rights do we support? Per our functional requirements, we can create posts and we can create likes. For our posts, let's assume that users create a post once per day. So we have 1 billion posts a day. We can assume 100,000 seconds in a day. It's not actually 100,000, but remember, we're doing back of the envelope estimates. So I can multiply that by 10 to get 1 million. That gives me 1,000. And then I'm going to take that 10 back. And I'm going to say this is 10,000 posts per second. Great. Got a quantity here. For likes, I would assume that users are liking posts more than they're creating them. In fact, I would expect that they're liking lots of posts as they're scrolling through their feed. So let's just 10x that. Let's say that they do 10 likes per day times 10 billion users. We have the same calculation here. And then ultimately, we're going to end up with 100,000 likes per second. This is an interesting insight here. Generally speaking, the write volume of our system is dominated by engagement or likes, as opposed to the post creation. So we're going to note that to the interviewer who's going to be impressed by our foresight. Now let's talk a little bit about reads. So for reads of our system, the only way for you to read is basically by searching. We don't expect users to search very often. In fact, I think even 1 a day is probably an overestimate, but we're just going to fudge it because these are estimates. And so we're going to have 1 billion users a day, making 1 search per day, 100,000 seconds. This is 10,000 searches per second. Now, note here that our original instinct that this would be a read-heavy system is incorrect. This actually is a write-heavy system. We're doing more writes than we're doing reads. And this kind of makes sense. Generally speaking, search systems are going to index a lot more things, and then the users are going to make sparser queries into that. So this is a really helpful insight for us as we go to design the system so that we know to put the appropriate attention on the ingestion, those things that we're using for the writes. A final quantity that we may want to estimate for this problem is storage. And so for posts, we're making 1 billion posts a day. We make 365 days in a year, and maybe we've got 10 years of history. We want to know how many posts are actually in our system. This would be somewhere around 3.6 trillion, billion, 3,650. So 3.6 trillion posts. That's a lot. That T is always kind of scary. And if we want to estimate the storage for those, then we have 3.6 trillion times 1 kilobyte per post, I think is a pretty reasonable estimate. Post has a bunch of metadata. Some posts are really short, hi mom or happy birthday. Some posts are really long. Let's just average them out. Now we've got a trillion, which is tera, and then we add an order of magnitude. So we've got 3.6 petabytes of storage for all of the posts. That's a lot of storage. And in general, that would probably cause us some problems. So for our design, what we want to do is figure out, do we need the entire post stored in our search system? Maybe not. And then if we do, can we figure out a way to use disks or some other scalable storage for this? Because keeping this in memory is going to be somewhat prohibitive. So in this exercise, we've realized a few things about our system. We've made notes to our interviewers so they can kind of see, hey, this person thinks about, the way that this system might actually behave. And we've got some real numbers that we can tie some of our discussions to, but we're not going to spend additional time here. We're going to keep moving. With the requirements and constraints of the problem in place, we're going to move to trying to set up the problem. The first step for us is to define the core entities of the solution. The core entities are kind of the nouns that we're going to use to describe the problem. And for some problems, this is going to be a very important step. It's mostly going to allow you to talk about the various interplay of nouns and resources in your problem. It's also going to clarify how the system actually functions. But for this problem, it's not that complicated. We have users, they create posts, they like posts, and we want to search them. So we don't really need to spend a whole lot of time elaborating on this, although listing them out can be helpful so that we at least know what's going on and our interviewer is on the same page. The next step for us is to start to define an API. In the ideal state, our API is going to cover all of our functional requirements. So everything that we want users to be able to do with the system, they need APIs to be able to accomplish. So that coverage is important from that aspect. API design is also really useful if it completely covers your functional requirements because it means your design is complete once you've implemented these APIs. So it's worth spending some time upfront here to design good APIs. Now, interviewers are going to vary depending upon how pedantic they want to be around your API design. Some interviewers can't wait for you to get to the high-level design. They really want to talk about scalability, and the API design they aren't too enthused with. Other interviewers care a lot about API design. They realize their last on-call was a total pain because the API design was not sufficiently emphasized, and so they might really hit you here. The point being, I would not skip through or skimp on the API design, but be careful about spending too much time here because in a lot of cases, there still is significant meat to your interview to get to. Now, fortunately for this problem, our functional requirements are pretty simple, and so we can kind of go through each of these requirements and see whether they map cleanly to an API. So our first requirement is that we must be able to create posts. And the most natural, restful way for us to do this would be to have a posts endpoint that we post to allow us to create a post. Nice and easy, albeit a little bit ambiguous with the HTTP verb. Same thing with the likes. What we want to be able to do is add or remove a like from a post. What we can do here is we can actually either add or delete an entry from /posts/ID/likes. What this is doing is it's basically nesting this resource, this likes resource behind the post resource, which is a great way in RESTful API design for us to layer these resources. Again, not the most important API, but it does cover our requirement. The final API that we need is to be able to handle these searches from users. Now, our searches need to take in a query, which is basically the keywords of our search, and it needs to have a sort. And maybe the sort can be either likes, or it can be sort by time. What this is going to do is it will map to our requirements and allow our users to specify that. It's also pretty constrained. Note here, I'm not allowing you to pass in facets. I'm not allowing you to pass in other things that might be relevant to this search. We're just keeping you to the functional requirements here. Now, these APIs seem simple, and that's a good thing. We don't want to overcomplicate this. So let's leave it at that and keep going. Now, the next stage in our process is we want to do our high-level design. And our high-level design is intended to satisfy our functional requirements in the most minimal way. What we're trying to do is basically make our system work before we optimize it, so we can avoid premature optimization. If we optimize first before it's working, it's going to be really hard for us to get that last step and make it actually functional. So we highly recommend that you first build a simple functional system before you go deeper. Now, it's okay if you jump a step ahead and you start with some optimizations. I'm liable to do that as well. But be careful about going too deep into optimizations. This is a really common mistake that we see from candidates. Now, for our first requirement, what we need to be able to do is to take in a request from our user to create a post, and we need to be able to store it somewhere. So one of the most obvious ways for us to do this is to create a simple load balance service. We'll put it behind an API gateway that will allow us to do authentication, will also allow us to do rate limiting and then routing, so we can actually have a singular endpoint with multiple microservices behind it. And then we'll have a database for our posts that we'll put here. In our post database, we will store all of the metadata around the post. And so things like its ID, the content, maybe the creator ID or the author ID, and then the created date. The sole point here is we store it somewhere. And this is not really the focus of our session. In some sense, we are expecting these to be outside the search functionality, but we'll leave them there anyway. Now, our focus is on search. And so I'm going to include a little stub here and just imply that I am going to be somehow updating search indexes when these posts are being created. That, as the posts are created, I'm not only persisting them to the database, I'm also letting my search service know that, you need to have these available for people to search. And that is post creation. So that's our first functional requirement. Our next requirement is that we need to be able to handle like events from users. And we're going to use a very similar structure here. We will take in a request to our likes service, write it to our likes database. And the likes database is probably going to have a very simple table structure. We want the post ID that's stored with it, maybe the person who's doing the liking, and then also when the like was created. Not super important that we have the right fields here. All we're trying to imply is that these are stored somewhere and we'll have them available should we need to query them. It is important that our like service is letting our search know when a like event happens, because we need to, in some sense, be able to update the sorting that we give to our users. Although I'm not going to go into that just yet because we're just focused on that second functional requirement of users being able to like a post. Now, our last functional requirement is to allow users to search. And it makes sense that we might set up a separate service for this. The reason that this is separate is because it's read heavy and it's going to be doing very different work than these services, which are simply writing to different data stores. And a beginner might assume that this search service should just read from our post database. If our post database was MySQL or Postgres, what we could probably do is just select from posts where content like keyword. And what this would do is it would go over every entry in the post table. It would grab the content for that post, and then it would run this grep, basically. It would try to find if the keyword is contained somewhere within the post. Now, this is not a very good idea from the get-go. And either A, you need to volunteer this to your interviewer, or B, you should probably try a different approach for two reasons. One is this does what's called a scan. This is going to go through the entire post table and look at every single post. We already talked about how we have 3.6 trillion posts. So that's going to be incredibly slow. And secondly, this like keyword is actually going to be very slow as well. What I need to do is go through the entirety of the content to go and see if that keyword exists, which is completely suboptimal. We're going to note that in this case, what we probably want to do is try to figure out how we can pre-compute. And the optimal solution here is to use something called an inverted index. An inverted index is basically asking, what would be the ideal data structure that I could read from in order to get the fastest possible searches, and then working backwards from that. So the ideal data structure would look something like this. For a given keyword, it would just have a list of the post IDs that match that keyword. If we pre-computed the results of all of our searches, then we would be able to return searches really quickly. So all that an inverted index is doing is it's taking the content of the posts and then breaking it apart into its individual keywords. And then for those keywords, it's going to associate them with that post ID. Now, if I sorted this table by the keyword, what I can then do is grab all the post IDs that match a given keyword, and I can return those back to the user. That is an inverted index. And so in a slightly more tractable variant of my high-level design, I would take all of my keywords and they would map to a list of post IDs, just like this. And then instead of reading from my post database, my search service would read from those search indexes. Now, just for clarity, I'm going to clean things up a little bit here. What we need to do as we're creating this keyword to post ID mapping is for a given post, we need to break it out into all its keywords. This is a process known as tokenization. Not necessarily important that you know that in a system design interview, although some interviewers might expect it. But the key thing is there is some compute involved. And more importantly, that tokenization needs to be consistent. So what we might do here is create a new service. We'll call it our ingestion service. And our ingestion service will be responsible for taking our posts, breaking them into keywords, and writing them into our search index. A really clever way for us to set this up is actually have our ingestion service read via CDC from our PostDB. That way, whenever a post is created or changed, our ingestion service knows about it, and it can then in turn go and update our search indexes. This eliminates the need for our post service to write directly to our search index and kind of clarifies things a little bit. I think we can move these around as well. We'll want to do the same thing with likes, but we'll talk about that in just a second. So now we have the ability for a user to get a keyword or input a keyword and get all the posts that match it in a reasonable time span. But the part of our functional requirements that we're missing is the ability to sort. Remember that users don't just want any set of posts. They want either the most recent posts or maybe the most highly liked posts in general. So we need some way of answering those queries effectively. Now, the beginner would probably do this. In my search service, I will go and query the list of post IDs for the keyword that the user's requested. And then based on the sort that they've specified, I'm going to take those post IDs and go to the post database or the likes database and grab either the creation date or the like count for those inputs. Then I'm going to sort all of those post IDs and return them back to the user. At small scale, this is okay. If you only had 5 posts, this might actually be a near optimal solution. But imagine a keyword where we have thousands or millions of matches. In those cases, we need to query thousands or millions of posts for their metadata or like counts. We also need to then go and sort all of that data before returning it to the user. So this is the beginning of a problem. I'm also going to note here that if we have millions of matches for a particular keyword, that means we need to pass millions of post IDs back to the search service. And this could be a problem. Remember, if a post ID is, say, 10 bytes, and we have 10 million post IDs, million is mega, 10 times 10 is 100. That's 100 megabytes of data that needs to be sent across the wire between our search index and our search service before we can go and return results to a user. We don't, in almost any circumstance, want to return 10 million results, but we need all of those post IDs in order to do that final sorting, because we don't know which posts are going to be the most liked or the most recent until we actually go and grab that data. Any place in system design where you're moving around requests that are order of many megabytes, it's usually a sign that something is broken and you need to rethink your approach. So how do we solve this? What's the solution? Just like the inverted index, it's useful for us to think, how could we arrange the data such that our reads are really quick and exactly what we need? And then what do we need to do in order to make the writes follow that same data shape? So the ideal case would be that this list of post IDs is already sorted. If our list of post IDs was sorted by creation time, then when our search service queried that keyword, we could grab the top 100 items and then return those back to the user. We don't even need to do any sorting in the search service. That would be the ideal. But remember that we support 2 types of sorts. We can sort by the creation date or the like count. So how would that work? Again, we sort in 2 different ways. The answer is no and yes. The no is you can't have a sort order that satisfies both of those. But what if we doubled up our keywords? What if instead we have an index, which is likes for the keyword, and we have one which is time for the keyword? In both cases, what we'll do is we'll use a Redis sorted set just to keep things simple. The score will either be the like count or the time. And then our sorted set will keep things in order and make our queries very fast. We can do this in log n time. Then when our search service is trying to field a request for a given keyword, given a specific sort order, it can go to our search index and either look at the like prefixed keys and sorted sets or the time prefix keys, and then just grab the top n items off of that key and return it to the user. The other thing that this allows us to do is we don't necessarily need to keep all of the post IDs forevermore. We can actually cap this. Maybe we only keep around the post IDs that have a like count that's in the top 100. Those are going to be the things that will actually return in our search results. Now, in order to do this, we are going to need to make a few adjustments. Notably, our like service needs to give our ingestion service a notice when a like event happens. Previously, we had that written directly into the search index. That doesn't really make any sense. We still need to store those likes in a likes DB, but let's go ahead and have some sort of cache that has all of our like counts. We can put this in Redis or something volatile because we don't actually need to maintain this forever. It is in some sense going to be a summary of the likes database. And whenever a like happens, we will increment those like counts and make the write to the database. Same thing with an unlike event. And then our likes counts can ultimately be CDC'd into our ingestion service in much the same way. Now, whenever a like count changes for a given post ID, our ingestion service receives that notice. And then what it will do is it will look up that post, it will grab its content, it will find all of the keywords that match, and then it will update the relevant indexes. This is still a lot of work. And remember, our like events are happening a lot. So this is in some sense a bottleneck, but our system now functions. We can basically return results for sorted keyword searches in a somewhat reasonable amount of time, which marks the end of our functional requirements. This system, while far from optimal, is the start of a solution for what we need to solve going forward. And that allows us to transition to focusing on optimizations and non-functional requirements moving forward. So the key to deep dives in an infra-style interview is to look at your system holistically and then identify those things that stand out as critical bottlenecks. The bottlenecks are oftentimes aligned with your non-functional requirements. And so it's probably a good place to start by saying, does this system satisfy my non-functional requirements? Let's go through a few of those non-functional requirements and kind of see how the system responds. The first non-functional requirement we have is that we want to maintain low latency and really high throughput. We've got a lot of users of this system. So we've got a lot of people banging up our search service and hitting up our search indexes. What can we do about that? Oftentimes, when you think about read volume, your initial instinct should be, is there some way for me to cache this? And remember, in this case, since the search isn't personalized, a lot of people are going to have the same searches. So for instance, when Taylor Swift breaks up with her boyfriend, people are probably going to search for Taylor Swift or whatever her boyfriend's name is. And they're going to try to get whatever those post results are. It probably doesn't make sense in this case for our search service to continue to hammer our search index in that case. What we probably want to do is have some sort of cache. And in this case, what we can do is we can check the cache first, see if the cache has a result. And if it does, we'll return it. If it doesn't, we'll go to the search index. And then when we get a new result, we'll store it in the cache. We want to keep the TTL, or the time to live of this cache, relatively low, because remember, we have a non-functional requirement that ensures that when a post is created, it appears in our search results within 1 minute. So our cache can't live longer than 1 minute, or we may return cache results when we need to be able to show a new post. That's where the power of having that 1 minute is really helpful. because it tells me what the TTL of this cache needs to be. Another thing that's kind of interesting here is that the search service, before that cache is populated, is going to make duplicate calls to the search index. So if for the first second, maybe before we return the initial result, we get 100 requests for Taylor Swift, then we aren't able to hit the cache for those 100 requests. So sometimes what can actually be useful is, instead of having an external cache, we actually move this cache inside the search service. That basically, and this visual is not going to be very good, but we'll deal with it. Basically, each search service will maintain its own cache. And that way, that search service will only have one request that goes to the search index for Taylor Swift at any point in time. And the number of requests that hit our search index is upper bounded by the number of search services we have. So if we only are making one request from each search service and we have n search services, then at most n requests are going back to the search index, which is an improvement. A even more optimal solution to this problem of very high volume and read throughput is to think outside of the boxes of our system here. When users are submitting requests to us, they're submitting them from all over the globe. And a very common setup for systems like this is to use what's called a CDN, or Content Delivery Network. A CDN acts like a globally distributed cache. You might have a CDN edge node, basically a server that might be down the street or downtown in your city. And that edge node will maintain a local cache of things that have the right cache headers in their response. So what this would look like is, when we return the first set of results for Taylor Swift, we are going to put HTTP headers that say this is cacheable for up to 1 minute before returning it to our users. That response is going to get returned via the CDN. The CDN is going to read those cache headers that say this is cacheable for 1 minute, and they're going to store it at that location that's downtown or at the end of your street. Then when your neighbor goes and makes that request for Taylor Swift, instead of coming all the way back to our search service, or what CDNs would call the origin, they will instead serve the result directly from the cache that they have available on that edge node. So you can use caches at every layer in your design. They can be local to your service. They can be distributed caches that are stored alongside it. They can be CDNs that are distributed globally. There's a lot of discussion about where you put data, but your instinct here should be, I need to use a cache because that's an easy way for me to blunt the read volume for something that's going to have a lot of duplicate requests. And I should think about what layer is going to be most appropriate. In many cases, storing the data and caching as close to the user as you possibly can is going to be more optimal than having finer grained caches, unless they can be reused a lot. The next challenge that we want to be able to handle is the throughput on the write side. Remember, per our estimates, that we are getting 10x as many writes as we are reads. So while our caches and our CDN is helping us with that read volume, we still are at the mercy of some pretty heavy loads that are coming via our post service and our like service. In the worst case scenario, we have bursts of likes or post creation. Maybe this happens around New Year's, or people expressing some sort of solidarity with a cause. And then our ingestion service falls over and dies. The solution for this is frequently for us to introduce some sort of async processing. Remember, we've got a minute to work with, which is a pretty long time from a system design perspective. So what we might do here is introduce Kafka into our design. And instead of having our ingestion service directly read from the CDC stream, what we'll do is we will have our post database and our like counts write to a Kafka topic. Then we can scale out our ingestion service horizontally and have it read from this Kafka topic. What this does for us is it allows us to scale independently, and it allows us to be behind for a short period of time in our processing before we catch up. Now, you'll want to make sure that your ingestion service can be spun up quickly. If we're depending on scaling out our ingestion service to deal with spikes, it can't be 5 minutes before the ingestion service starts up. But fortunately, the ingestion service is stateless. What it's doing here is it's taking a request, it's basically taking a post ID, doing some lookups, doing tokenization, and then moving it into the search index. So it doesn't need to maintain any state. That might take some time for an ingestion service to start up, which gives us a little bit more play. The other nice thing about Kafka here is we can have some retention. So if our ingestion service were to fail, we can spin up a new ingestion service and reread from the offset in that Kafka topic to make sure that we aren't missing anything in our search index. So in these places where we need to deal with really high write throughput and we need some fault tolerance, Kafka is usually a very good option, and in this case, it's a perfect fit for our ingestion service. One interesting thing we identified with respect to the write volume earlier is that the like count changes are going to be 10 times as frequent as the post creation events. We're going to see 10 times the events coming from this leg versus the post creation. And that's really interesting because as we think about scaling, a lot of those like count events don't actually change what are displayed to the user. If we have a brand new post for a keyword, it will always be at the front of the line for the search results if we're sorting by time because it's the most recent post. But if we have a like on a post that used to have 0 and now it has 1 like, in a keyword that already has posts with millions of likes, it's not going to change a thing. In some sense, the like count events aren't all that impactful. They're not as important. To illustrate this, let's pretend that we've got 4 posts. ABC has 1 million likes, DEF has 10 likes, GHI has 1, and XYZ has 0. The ABC post is going to get a disproportionate number of the like events. If it has 1 million likes now, it's probably getting likes every second. But it's not changing the ordering. Those likes don't really mean anything. On the flip side, if DEF gets 1 more like, that's material for it, but it still isn't going to change the ranking. So what can we do about this? Well, one thing that we can do, and this would be what many candidates will propose at first, is we can batch the like events. So what we could do here is when likes happen, we will take a 30-second window and we will try to sum up all of the changes that happen over those 30 seconds. And then when the 30 seconds have expired, we can flush them over to our Kafka topic to be processed by our ingestion service. We can do this with an off-the-shelf solution like Flink, or we could potentially do this by stringing together Kafka topics, where we could have one Kafka topic here that would store the raw likes, and then we would have a batching service that read for 30 seconds, batched them up, wrote the result, and then stored its offsets. This is basically what Flink is going to be doing under the covers, but the key thing here is we could batch them. Now, the problem with batching is that it's only really going to be useful for ABC. ABC is the only one that's going to get light throughput that matters at a 30-second interval. DEF is never going to get post or like volume that's going to change second to second. So the batching will always be either 0, there will be nothing in the batch, or it will be a batch entry of 1. And we should expect that the vast majority of our likes on the platform will happen across this tail, things with lower number of likes, than the strictly viral posts in the head. So while the batching approach will help us, it won't help us that much. So what can we do instead? Well, another solution that we can do is we can take the logarithm of the total number of likes. Instead of having 1 million, we can record this as, I don't think this number is right, but 2 to the 16th or 2 to the 4th or 2 to the 0th. Now, whenever the exponent changes, we can store that in our search index. So what we'll store instead of the million likes that we previously had for ABC, we'll instead just store 16. In the like service, we will look at counts that ever cross a order or a power of 2, and then only kick those entries into our Kafka topic. Now that will mean that our search index only has granularity at powers of 2, which is pretty useful for sorting. It's going to make sure that the hyper-viral posts are always at the very top of your list, and the posts that got next to none or 0 engagement are at the bottom. But what it's not going to do for you is provide a precise ranking. So what we can do to augment this is we can store in our search index the powers of 2. We're only writing the powers of 2, so we're writing dramatically less number of events. And then in our search service, when we retrieve the post IDs for that keyword, we can then go and grab the up-to-date like counts and use those to resort the final list before we return it to the user. The idea here is we're keeping an approximation in the search index. We're keeping something that's mostly correct, and then we are re-ranking it or correcting it in that final search service before we return it back to our end user. This would be another way to reduce the volume of writes that we need to make into our search index. The last problem that we have to handle with respect to write volume is just making sure that this backing store, in this case Redis, can actually handle the volume of writes that we are pushing. The volume of writes in this instance is actually a little bit higher than you might expect. While our posts are coming in at 10,000 transactions per second, and our likes are coming in at 100, we did do batching, and we're also taking the logarithm of the likes, so we would expect this volume to be dramatically smaller. But we increased the number of writes by virtue of us tokenizing these posts and writing to multiple keywords for every post. So for happy birthday, we're going to write to 2 keywords, happy and birthday, with the same post ID. If we have a really long post, we would of course drop words like a and the and things that are not all that meaningful, but it might be the case that a post has 100 keywords, in which case the write volume is 100x what either the post writes or the likes that are happening, which may be too much for a single host. With Redis, there is a lot of throughput because it's all in memory. And the benefit of choosing Redis in this case is that we really don't need durability. In some sense, all of our likes are stored in a database, all of our posts are stored in a database. If we really needed to, we could recover these indexes by building them from scratch. So they're volatile, meaning we don't need to store them. But that doesn't necessarily mean that we get infinite throughput just because it's in memory. Redis's read and writes are approximately 100,000 TPS for a single core or a single node. And in this case, we might be exceeding that. So the trivial thing for us to do here is to use Redis cluster, where we basically set up many Redis nodes, and then we spread our keys across them. With Redis, your choice of key is basically your choice of partitioning or sharding strategy. So you will, in some sense, choose how you name your keys depending upon how you want them to be laid out in your cluster. The most obvious thing for us to do is to use the keyword as our partitioning key. This would mean that on one Redis node, we have all of the posts that contain the word Trump. And on another Redis node, we have all of the posts that contain the word Taylor. And then our search service is going to choose the node that contains the keyword that the user is searching for and send the request to that node. It's pretty straightforward and it makes a lot of sense. The problem with this is if one keyword is getting a ton of writes, people are creating posts a lot or liking a lot of posts around Trump or Taylor. In that case, we are going to be making a bunch of writes to the same Redis node. Now, in practice, we have to be doing this pretty aggressively. In some sense, the number of writes that are happening for Taylor Swift need to outnumber all of the writes that are happening for all the other keys in order for this to be really a problem. But it's conceivable that for certain time periods, that might actually be the case. So what else can we do in terms of partitioning? Another idea that we can do is we can take the post ID and include it as part of the key. So instead of just like keyword, we can include a shard modulo. So maybe we have like one keyword or time two keyword, where that number is a number between 1 and n, maybe between 1 and 100, which is the remainder after we divide the post ID by some number. What that's going to do is it's going to multiply the number of sorted sets that we have for a given keyword. So instead of having one single key that is all of the posts sorted by like that contain the word Taylor, now if n is 4, we might have 4 of those keys spread throughout our cluster, so on different nodes. That's nice because it means the ingestion service is writing to different nodes even though the posts may all contain the word Taylor. But it has a downside. Now our search service needs to call to 4 separate nodes in Redis. It needs to retrieve all of the posts for each of those nodes, and it needs to do sorting on its side as it merges those together. So what we're basically doing here is we're trading off write volume that we have into our indexes on a single node for read volume across all of our nodes. We're basically making more work for our search service. The great thing about this is we have a parameter. We get to choose that n. And so if we encounter that situation where Taylor is a really hot key in a particular node and we need to adjust, we can just increase our n. And that will mean we may need to scale up our search service or we may need to handle our caching differently, but it puts more stress on this part of the system versus our ingestion side of the system. So expect in an interview setting for your interviewer to ask you questions around what is the partitioning or sharding strategy, and think about the options. Usually when it comes to writes, taking the identifier of the thing that you're trying to index is a good idea to spread things out. But as it pertains to reads, you may want to partition based on that thing that you're reading. This hybrid situation is the nice middle ground in case neither one of those is working. And you should reserve it for those situations where you need to kind of optimize both. One more deep dive that we might run into is how we can handle the storage requirements of our search indexes. In general, we can restrict the amount of space that's required here by limiting the number of post IDs that we have for every keyword. That means that the size of our search indexes is the choice of n, basically the number of shards that we have, multiplied by the number of unique keywords, multiplied by the number of capped post IDs that we'll store. So we may not store all 10 million post IDs for Taylor. Maybe we only store the top 1,000. And what that will do is it will restrict and make sure that the size of our search index is not growing unbounded. But even still, this is going to be a lot of memory. So what we might think about is how we can separate hot data from cold data. A lot of systems look like this, where users are disproportionately reading from a subset of the data, the hot data. And the cold data, we sometimes want to keep around in case we need it. But generally speaking, we don't expect very high performance on it. It's kind of like if you had a closet that you put old files into. You're not going to put things in that closet that you access very often, but you'll have it and it will take you a while if you need to go and retrieve something that's really important. So we can apply that same concept here. What we need to do is basically have a way to have these search indexes moved into a colder storage. One way to do this is to use S3. What we can do is find keywords that aren't being written to very often and aren't being read very often, and then evict them to this cold storage. Then, when our users are searching, we would first hit up our hot indexes. These are very fast in-memory indexes. And then if we don't see any results there, then we can go to our cold storage to see if we can pull something out of the filing closet for that particular user. That leaves the only real problem in figuring out which are those things from the index that we can evict. One way that we can figure this out is by using something called count-min-sketch. Count-min-sketch is a cool data structure that provides an effective way to approximate the count of a set of items. And you might have heard of it if you've done any research into Bloom filters. It's a close cousin. Basically, what count-min-sketch will provide for us is an upper bound on the number of times an item has been seen before. So what we can do is we can ask count-min-sketch for an item, let's say Taylor, how many times has it been seen before? And maybe count-min-sketch responds to us that Taylor has been seen 5,000 times. That doesn't mean that there are actually 5,000 searches that have been made around Taylor or that Taylor appears in 5,000 posts. It means that Taylor appears in at most 5,000 posts. But this is a pretty big number and a good approximation. On the other hand, maybe Stefan only appears 12 times in our data set. So what we can do with count-min-sketch is with a small amount of memory, we can count up the keywords that are appearing in searches and then also that are being written in our ingestion. And then we can look at our search index and we can scan through all the keywords and find out which are the keywords that are accessed the least often and pull them out of the search index and put them in cold storage. Now, when searches come in, they'll find that they're missing from the search index, they'll look for them in cold storage, and we'll return a result which is slower for that user, but still going to get them the results that they're looking for. Count-min-sketch and probabilistic data structures like it are oftentimes a powerful tool in system design, in part because we don't need an exact count here. What we're really trying to do is make sure that we are pulling away things that are likely to be uncommon, as opposed to things that are definitely only represented n times, which we can't answer with a data structure like count-min-sketch. The final deep dive that I'm going to touch on here is something that your interviewer might do in a setting like this. In this case, they might ask us, okay, we handle individual keywords, but how about multiple keywords like Taylor Swift? How would we handle requests like this? These are called sometimes n-grams, or this one is a bigram, 2 words. But what we want to do is find all of the posts that contain the word Taylor and right next to it, Swift. So how can we do this with our existing system? The way that we would do this with our existing system is the request would come in with the keyword Taylor Swift, and we would break that into Taylor and Swift. We would go look up all the post IDs that contain Taylor and all of the post IDs that contain Swift and return them back to the search service. That's the superset of all the posts that potentially could match this query. Then what we need to do is go to the post DB and grab the content for all of those posts, and then manually scan through all of them to see if Taylor and Swift are right next to each other in those posts. What we don't want is to grab a post that contains Taylor was next to the Swift River, which is clearly not a match for this query, but has both Taylor and Swift in it. So we need to be able to filter those out, which we can do in a final filtering stage before we go return those back to the user. Now, this would work, and given that this query is going to be less likely because it contains more words, maybe this slowdown is acceptable, but we can probably do better. So what might we do? Well, one thing that is possible is we would take our existing search indexes and also insert into them bigrams. So we would have an entry for Taylor Swift. If a post contains 100 words, it has 99 bigrams. Just take that window, first and second, second and third, third and fourth, and move it all the way across your post. So by adding bigrams to our search index, we would theoretically only increase the search index size by 2x. Now, that's in theory, Because in reality, what happens with bigrams is they are far more unique than unigrams or single words. There's only so many words in the English dictionary, or only so many trademarks that are out there that are a single word. But the combinations of two words, there's substantially more. And so what that means is that in our search index, we would actually have many more entries than just our single unigrams. So this is a place where we're going to end up making a space versus lookup time trade-off. Now, one thing to note, we had just talked about how we can use CountMin Sketch to find search keywords that are uncommon or not searched very often. We can use that same approach to try to filter down the bigrams that we actually want to write into our search index. We always have the option to go and do this intersection between two keywords and then go and manually scan through their entries, the slow option that I just talked about. So what we want to do is make it fast in the places where people are actually searching for it. So what we can do is we can go and query our CountMin Sketch to go and find for every candidate bigram, every pair of words, how often they appear in people's searches. And then we can write that bigram into our search index only if that value, that count, exceeds a certain floor or threshold. What this will allow us to do is avoid those situations that we're writing a bigram that nobody will ever search for and only creating those bigram entries when they actually count. That's a nice middle ground here between spending a lot of storage or eating a lot of latency. And again, these types of middle ground are kind of the bread and butter of system design. I'm going to go ahead and stop here just to summarize. In general, this question gets asked of all levels, from mid-level all the way through staff engineers. For mid-level candidates, mostly interviewers are looking for, do you have some concept of an inverted index? This is usually a pretty fundamental concept. And can you put together the pieces to make this workable? It's not required that you get to anything near optimal, but in general, your interviewer wants to see a somewhat working system. Senior candidates are going to move much further down the road. They're going to start to identify bottlenecks. They'll have solutions. They may not be as clean. Staff level candidates are going to have seen systems like this before. They're going to have some in-depth knowledge about things like Elasticsearch and how it works. If you haven't already, I'd recommend viewing our video on Elasticsearch. I think it does a good job of breaking down how it works, both from a user perspective and then some of the data structures that are under the covers. In this interview, we covered a lot of different concepts. We not only went through the Hello Interview delivery framework, we covered caching and the various layers that it can happen. We covered inverted indexes and how you can customize your data so that way your reads are fast, even if it compromises some on your writes. We covered hot and cold data partitions. We use CountMin Sketch to calculate statistics. We've basically hit on a bunch of different techniques that I hope you'll find useful in other problems, especially more infra-style problems that you might see in the future. I've really enjoyed this time. If you've got questions about this problem, please drop them in the comments. We also have a write-up on our website, which covers slightly different ground, but mainly the same thing that might be helpful for you as you work through your interview prep journey. And especially if you'd like to work with expert coaches who can help simulate system design interviews and kind of help you through complicated problems, highly recommend booking a mock interview with some of the coaches on our platform on Hello Interview. I'll include a link in the description. But thank you so much for the time. And until next time, I'll talk to you later.